Up until now, in physics, everything that you have studied, mass or moment of inertia, etc., has been a property of an object. We're now going to deal with something new. We're going to talk about numbers that are properties of a location, a point in space. It might even have nothing else there except for the field that we're going to talk about. What is a field? It's a value at every location. So the temperature everywhere in this room, the concentration of oxygen molecules everywhere in this room. At each location, there is a value, which is how concentrated it is. So you can imagine it as a number at every single point. And those numbers are effectively property of the location. Density. Air density changes as you go up through the atmosphere. So you could have different densities at different locations, and so you could have a density function, which is the scalar field. Really, that's all a field is it's a function that takes a location as input and gives you out a number. There's two new ones to be dealing with. One is the gravitational potential, and the other is the electric potential. Now, first of all, that's a terrible name because it makes you think of potential energy, and it's not the same thing. It does not have the same units. Gravitational potential is actually gravitational potential energy per mass, per kilogram. Electric potential is electric potential energy per charge, per coulomb. It's a terrible name. We won't talk about gravitational potential very much except as a basis of comparison. And electric potential we're going to talk about a lot because it's voltage. And I will refer to it as voltage as much as possible because I think that's a much better name. It's much clearer. Now, a voltage is a scalar field. Every location has a voltage. It's a property of the location. Even in empty space, if you have a charge nearby, that's going to produce a voltage over here. It's a way of describing the effect of the charge on the space around it. So those are scalar fields. There are also vector fields. Now, vector fields give you a vector at every point. One of the easiest ways to make a vector field is to take the gradient of a scalar field. So if you have temperature, the temperature gradient, this is a symbol del, it's a vector operator, we say. It turns this function into a vector. What is that vector? It says which way is warmer. Concentration gradient, which way is more concentrated. So that gives the direction, and then the magnitude is how quickly is it growing? Like what's the slope when you move in that direction? Like change in concentration over change in x, if x is the direction of where it's growing the most. So it's really, gradient is a slope in 3D. You could also make a vector field without a gradient. You could have the velocity in a fluid at every point, right? You could have some fluid flowing around an object, maybe there's some turbulence, more complicated behaviors. Every point, the fluid has a certain velocity, so you would have a vector at every single point. And that one doesn't particularly come from a scalar as far as I know. Here's the confusion in vocabulary. Any physics book that you pick up for the intro level is going to talk about gravitational field and electric field. They mean the vector field. They do not mean these scalar fields. All right, these scalar fields don't even get mentioned half the time. The gravitational field G, we didn't stress it last semester because it already had another name. It's the acceleration due to gravity. Why is it a vector at every point? Well, at here, it's 9.8 downward. And here, it's 9.8 downward. And everywhere in this room, there is a vector, 9.8 meter per second squared, pointed downward. That's a vector field. It's a uniform vector field. In fact, the only two kinds of fields you're going to have to worry about, vector fields, are ones that are uniform. They all point the same way, like gravity pointing down everywhere. Or the ones that are radial, pointing outward from a point or inward towards a point, like Earth having a gravitational field that points inward. At every spot, there is a vector that says this way is down, and this is how much you will accelerate if I let go of you. So the gravitational field is a property of a location, just like the gravitational potential. Now, there's a relationship between them. The gravitational field is actually the negative gradient of the gravitational potential. And so they refer to this as a scalar field, and this is a vector field, which is confusing. When other books talk about it, this is what they mean by the gravitational field. They mean the vector field. And likewise, electric field. You will be taught about electric field after, in like lecture 4 or 5, something like that. But they will be talking about it in advance. They'll just keep referring to it as the gradient of the electric potential. So you're going to hear that phrase a lot, electric potential gradient, electric potential gradient. Well, electric potential gradient is electric field, really. The electric potential is voltage. So voltage is energy per charge, joule per coulomb. And the electric field is the gradient of that, the negative of the gradient of that. So electric field points towards lower voltage. And positive charges have high voltage near them, and negative charges have low voltage near them. So if you put a positive charge near a positive thing, there's going to be a high voltage here, and that way is going to be downhill, and that's the direction that the proton or whatever is going to go. So these are very important ideas, and I wanted to get them very straight for you. Scalar field versus vector field, a number at every point versus a vector at every point. And you can make some of these from these by taking the gradient. If you have numbers everywhere, you can say, well, how fast is it changing? And that's about it.